How you guys doing? Keep admitting people. Good. Like we're getting people in. Hope you guys had a good weekend. I wanted to let you know, in case you didn't already see it, that the grades are posted for the homework and also for the quiz. This is all on Gradebook. Okay. If you can't read it for some reason, send me an email and we'll take a look and see what's going on. I graded the quizzes and the homeworks online, and I wrote like comments on them, using like an online program for it. You should be able to see the comments like on the quizzes and on the homeworks as well, so you can kind of get a feeling for like where the grade numbers came from. If you can't see the comments that I wrote, like the things that went wrong or whatever, let me know, because I'll take a look at maybe a setting in Blackboard that I have to set to make sure that you guys can have access to that. But that should be available for you. Certainly the grades are there. Your grade running average for the semester is listed. I think it's called final grade. I have that set up with all of the weights that we have right now. So for our, like how much our quizzes are weighted, I haven't dropped our lowest quiz yet because we've only had one. So I'm going to wait probably till the end of the semester before I start dropping the quizzes, just to kind of give you an idea of what to look for. So that final grade column should be set up for you to give you an accurate representation of what your grade for the semester is. And yes, if you got that on your grade will be higher than 100. I do actually give points. I don't max out at 100. That's kind of the whole point of extra credit. Anyway, so keep that in mind if you want to take a look at that. Looking at the syllabus here, I want to call your attention.
Question, where are the grades posted on Blackboard?
Yeah, so I have them posted on my view. It's listed, it's called Gradebook, right? So if you go on Blackboard, there's a thing, like an option. For me, it's along the side column. And then
I don't see it there.
You know, I'm not sure how it's going to look for you. On my screen, it shows up on, there's like that page that has like our sort of our main dashboard, and then there's all the different like options along the side, like assignments and whatever. And then one of the things on it is Gradebook. It's where you upload it.
Anything about grades.
Upload quiz.
Could you repeat that?
Where did you upload your quiz? You did the quiz work
through assignments.
Oh, you did it through assignments. Okay, I see them all on. Okay, I see them all on Gradebook. Let's take a look. Maybe we'll talk after class and we can kind of brainstorm about it, and I'll show you like we'll talk about like what I see, because it's something that shows up under, for me on my Blackboard page. It shows up on as it looks like, it's actually called Gradebook on the side. Now I'm in Blackboard, not Canvas.
Yeah, hold on. Somebody in chat said something.
Let's see. I'm not looking
on the right.
Yeah, give me a sec. Go to the drop down on the right and right click on the sheet with the check mark, should be there. So that's, I think, you're talking about like if you're actually in Gradebook, right? Now, can you actually get to Gradebook and see the Gradebook part, or you're just
I can't see the Gradebook, but I can see the grades on the actual assignment, so I guess that works.
Okay, great. So if you can see the grades on the actual assignment, so what he's talking about, good. So you can actually get into the Gradebook. That's good.
Yeah.
So what he's talking about is there's like a little, for me, it's got like a little, like a down arrow. And if I click on that, then it'll bring up the actual file itself. I'm not sure how it looks for you, but the file is actually attached in your Gradebook. And you can see, you should be able to see my comments on there too.
Okay.
We can talk about it after class if you want, and then
sure.
kind of go through it. Let's see. Just anyway, so I wanted to call your attention. We're bumping up some stuff. So I'm looking at the syllabus right now. 2.6, right? We're going to do today. That's our Combinatorics chapter. That's to make sure that we're all on the same page about how Combinatorics works. Some of you may have had it, some of you haven't. It's really helpful because it does form the basis for algorithms for how we're calculating things in the background. And then we'll start in on chapter 3 this week. On Thursday, just like we did for the quiz, right, we're going to have a 24-hour window. We have our midterm exam. This is our first exam. We've got 3 exams, okay? So this midterm exam will most likely cover everything up through chapter 3.4. Initially, I had said it would cover through 3.5, but I think 3.5 is going to get bumped until next week because we're bumping 2.6 until today. So keep that in mind. So what will happen on Thursday is, again, at midnight, your homeworks will be due, okay? But make sure that you're doing all the homeworks like every day after class, because, you know, like everything, the homeworks are just going to keep accruing, and they're all going to be due on Thursday. And then we'll have our test again like we did with the quiz, only you'll have more time. The test will be the whole length of time, okay, for the class period, plus you get an additional 15 minutes to upload stuff, okay? And by the way, I really appreciated everybody uploading things into PDF format. That was very helpful. It's really hard. I can't really grade it unless it's in like a PDF format. I certainly can't read it unless it's in PDF or JPEG, but PDF allows me to actually grade it. So what I'm going to do today is like after class or after office hours, depending on how much time I have in between things, I'm going to upload some resources for you, some old exams from previous semesters, so that you can get a feeling for what was asked previously. When I've taught this in the full semester, like fall or spring semester, the exams had more material because we only did like maybe 2 exams instead of 3. So I'll tell you which questions to focus on because I'm only going to be covering certain things. So take a look for that. I'll send a note out on the announcement when those things get posted so you know to look for that. That'll be under our course materials, like, you know, basically practice stuff for exam 1. We're going to have office hours again this whole week like last week. So if you wanted to come to office hours, you can ask about homework problems or old exams or whatever you want to talk about. Is totally fine. Okay, so that's administrative stuff. Keep that in mind. Thursday, homework is due. The first exam is happening. And then also if you have old homework that you want credit for, I believe you can upload it back into the old homework part because I think I set it up for unlimited uploads. Just send me an email because I'm not going to know to look otherwise. Okay, send me an email that I should look for it, and then I'll take a look for it on Thursday or Friday when I go to grade these things. Okay, all right. So with that said, let's go ahead and get started on chapter 2.6. Let's get this set up here. I think we're all set. Good. All right. So chapter 2.6 is called Combinatorics. Okay. So combinatorics essentially gives us a set of algorithms and a set of rules, right, for how we're going to count different combinations or permutations of events within a given space. Okay, so we've got 4 basic rules that we're going to cover today. Okay, so these are going to give us algorithms for counting and ordering. And the different rules, we're going to use one rule or the other depending on like what's being asked in a given question. Okay, so, you know, depending on what we're being told to take a look at, we're going to know which rule we're going to need to do. So let's go ahead and jump in with these basic rules. So the first one, and you may recognize some of this stuff as we're going along because we've been actually employing some of these things, and you'll start to recognize some of the ideas that we've been doing. So the first rule is called the multiplication rule, and I'll put a box around it so we know it's important. Okay, so our multiplication rule says this, we're going to use this for counting ordered sequences. Okay, so for example, we've been doing this like we've got 2 dice are rolled. This as an example. Okay, we've got the result of die 1, we have the result of die 2, right? We built up that whole table, right? Got die 1, which is, say it's a 6-sided die. I've got all these possibilities. For die 2, it's a 6-sided die, all these different possibilities. And then total, my sample space. Okay, we're going to talk about where that total sample space comes from. Okay, so let's write down our rule and then we'll talk about it. So this says if operation A is like I'm rolling die 1. So if operation A can be done in M different ways, okay, so it's a 6-sided die. My operation A is I'm rolling die 1. I can get 6 possible outcomes, okay, because it's a 6-sided die. So operation A, for example, I can roll it in M different ways, and and if operation B can be done in N different ways, right? So operation B is like die 2, okay? I'm going to roll it. It happens in this particular case when I have 2 6-sided die that M and N are equal to each other. They may be equal, they may not be equal. It's going to depend on the nature of the question. Okay, if operation A can be done in M different ways, operation B can be done in N different ways, okay, then the sequence we're going to write it like this. Operation A, operation B can be done in M times N different ways. Okay. We saw this with the two dice, right? I had die 1 had 6 possibilities, die 2 had 6 possibilities. We built up a table that had 36 possible combinations. 6 times 6 gave us 36, just as an example. Okay, so in this case, and means to multiply. Okay. All right, so it's just kind of, I'll just enumerate it out really quick just to kind of look at it. So I'm going to write operation A. Right. So operation A has 1 possibility. I'm going to write operation B here. So when I have operation A, my first possibility on operation A, I can do 1, 2, 3, 4, all the way down to N. 2, 3, all the way down to N different possibilities for operation B. Now my second possibility on operation A, I can do again 1, 2, 3, all the way down to N. Right. You can see where this is going. I'm going to keep going all the way down to M. And this one's going to have N different possibilities, right? So on my operation A side, I have M possibilities. On my operation B side, I've got N, so on and so forth, all the way down to N, right? So when I add up, right, add up all of these things here, my total number is M times N, total number of possibilities that I can do from operation A and operation B, okay? Let's start taking a look at some examples. So I'll pull out my example page, my lecture example. So example 1, right? Let's just read it and we'll talk about it. So Braille, many of you guys have heard of Braille before. So Braille is a raised set. It's got 6 bumps, right? And then a blind person can use Braille to read. Okay, so they're gonna scroll their finger over a sequence of 6, it's like a block of 6, a block of 6, a block of 6, and it's gonna help them to read. So they're using their fingertips to help them to read these 6 here. So Braille is a tactile, meaning touch, tactile representation of sounds and words, okay? And it's a set of 6 dots in a group that are raised off the page, okay? So we can do combinations of raise and not raise, okay? And we can generate a whole bunch of characters, okay, based on this set here. So a number of characters can be represented. So what we want to find out is what's the number of characters that can be represented in Braille, given that we're doing 6 dots, they can be raised or not raised. So let's start to kind of write down what our possibilities are here. So first I'm going to write out our Braille characters. So I've got, they kind of look like this, okay? And then they're numbered like this, 1, 2, 3, 4, 5, 6, okay? So each one of these is going to be a space where I'm going to raise, I'm going to like punch something through the page so that it's going to be embossed. When I touch it, it's going to be a little bump. So it's going to go in order, 1, 2, 3, 4, 5, 6. Okay, so 2 options for each space, right? I can do raise or not raise, okay? So let's just kind of start to enumerate what things are, right? And then it'll kind of help us picture what we're trying to do. So I'm going to start to enumerate. We won't, the whole purpose of coming up with these algorithms is so we don't have to enumerate, but as we're learning it, we're going to enumerate what we can so we can start to build a picture of what the algorithm is, okay? So I'm going to talk about what space am I in, and what's the outcome, and what are the number of choices. Okay, just so we can kind of think about it that way. So if I'm in space number 1, right here, right, I can raise it or not raise it. Okay, not raising it means it's just flat. Okay, so the number of choices I have here is 2, right? Space number 2, it's going to be the same thing. I can raise or not raise that spot. So I have 2 choices there. Same thing for space 3, 4, 5, and 6. Right, I can raise or not raise. I've got 2, 2, 2, and 2, 1, 2, 3, 4, 5, 6. Okay, so now I've got all these different possibilities. I'm going to multiply all these together, right? So when I multiply all these together, right, 1, 2, 3, 4, 5, 6, 1 for each space, I'm going to get 2 to the 6 different possibilities for what I can do, which is 64 total possibilities. So those are total possibilities that I can do. Let's just talk realistically here for just a minute. One of those possibilities is not raising any of the bumps, right? So one possibility is not raising all 6 spaces, right? So it's completely flat on all these 6 spaces, which doesn't make a whole lot of sense for a person who is using this as a tactile language. If there's nothing there, how can they tell that there's nothing there, or if it's just a gap in the page? So it's not a very worthwhile piece of evidence. So really, in reality, Braille has 63. We discard that one. Okay, so it has 63 total possibilities. Okay, because one of them really is meaningless in terms of what our audience is. So these types of possibilities, so this includes our 26 letters of the alphabet. We're going to get some punctuation, right? So some of these I can encode as like an exclamation mark, for example, right? And some of them are also things like we can get very specific phonemes, what they call phonemes. So word sounds like ch or sh, you know, the, things like that. I can encode those also, because obviously 63 possibilities. I only have 23 letters of the alphabet, but I want to be able to include more so I can encompass the whole language that we're trying to do. So, okay, that's one way to think about our multiplication rule. Okay. Actually, I'll leave this up here for you guys to finish writing it down. I can't tell if it's writing. Give you guys a minute. Okay, so next one, example 2. Okay, example 2 says, all right, let's talk about it. We're going to read it and then we're going to talk about it. So we have zip codes, right? Zip codes have 5 digits, and I put a plus here just to say we're going to do, this is like an and. So this is an and sign, but really the zip codes have 5 digits, a dash, and then 4 digits. Okay, so I've got 5 digits and 4 digits. So for a total of 9 digits, okay? So each digit can be a number in the range 0 to 9, right? So I've got 10 possibilities, and I can have duplicates, right? I can have all 9s or all 0. I mean, in reality, zip codes are coded very specifically to represent geographical areas, but possibility-wise for math, okay, we can do it 0 to 9 for each spot. So we're going to define some things, right? We've got our event space that we're defining, right? So n of t, t is our total number of possible 9-digit zip codes. Okay, that's the total sample space that we can possibly have. A is an event within that, right? And n of a is how many do we have, the number of. A says we want to do all possible zip codes with at least 1 7 in the first 5 spaces. Okay, I have to have at least 1 7. I can have all 7s, I can have 1 7. And then A says, I only care about the first 5. I don't care what's going on in the second 4. Okay, so I can have all 7s or no 7s in the second 4, but I need to have at least 1 7 in my first 5. B says, right, I want to do all the zip codes with at least 1 7 in the second, I'm sorry, that should be 4 spaces. That's a typo. Second 4 spaces. Okay, you guys see that's a typo. In the second 4 spaces, right? Now, again, I don't care what's happening in the first 5. Okay, it can be any combinations of things, but I need to have at least 1 7 in the second 4. Okay, so what we want to do, our goal for this problem is I want to find n of t, n of a, n of b. So the numbers of t, the number of a, the number of b. The numbers where a intersects b, and the numbers where a, oh, sorry, that's another typo, a union b. A union a, it's not very interesting. A union b. Okay. Okay, so let's start thinking about what we have. Okay, so I'm going to write down, start taking notes, start kind of to think out loud like what I need to do. So I'm going to go n of t. I'm going to start with that one. So I've got 9-digit spaces, and I want to incorporate all the possibilities, right? I have 10 numbers that I can include, 0 through 9, 10 numbers, and I've got 9-digit spaces to include from. Okay, so I've got 10 numbers for each space. Sometimes writing down what you need to do, like just in words first, can help you start to think about like the math that you need to do. 9-digit spaces, I've got 10 numbers for each. And this one I can do with repeats. Right, there's no restriction on that, right? You want to be able to have 0, 0, 0, 0. Doesn't make much sense, but you can. So though I can do with repeats, which means I'm going to go 10 times 10 times 10, because 1 for each space. 1, 2, 3, 4, 5. This is for my first 5. And then my second 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So I can have 10 digits in the first space, 10 possibilities in the second space, so on and so forth for the 9. So this is 10 to the 9th, okay, as my n of t. Okay. Oops, let me make that clear. 10 of 9. So it's important we're going to do this one first because we're going to do complementary sets, because at least one, right, is going to be the complementary set where I'm going to say essentially the total minus no 7s, right? So kind of think in terms of that. So I need to come up with the total number first. All right. So set A, we'll talk about A first. So set A, I need to have at least 1 7 in the first 5 digits. So as an example, it could look something like this, right? I can go 3 7 2 1 5 minus, I don't care, 7 1 4 6, right? I don't care what's going on in the second 4, but I'm looking, I need to have at least 1 in my first block of 5, okay? So this is going to be, I'm going to do my total number, right, minus basically the set with no 7s, okay? So the total number that I could possibly have, right, is going to be 10 to the 9th, we just calculated that originally, minus, right, I'm going to have, let's write it out first and we'll talk about it. Okay, this says, right, I have no 7s at all, times, now I have to take into account what's going on in the other 4, okay? So let's just write down this bit here is, this is total number of possible. This is no 7s in first 5 digits. This is any possible number in last 4 digits. Okay, that's our set A. And this is going to give us, right, at least 1 7 in the first 5, okay, and any possibility in the second 4. All right, so we're going to do the same thing for part B. Let me scroll this up. All right, so set B. So as an example, just to kind of get a clearing, let's see, it's going to look like, this isn't exhaustive, but it's just going to give us an idea. 9, 4, right? I could have a 7 in the first 5, it doesn't matter, minus 0 7 2 1, but I have to have at least 1 7 in the second 4. I can have all 7s in the second 4, but I have to have at least 1. This we're going to do again a complementary calculation, right? So this, I'll write this out as NA. Put a block around that one so you can keep track of it, and then we'll do this also for NB. Okay, so the number in B says we're going to do it again. So I've got my total possible numbers, right? Minus, now I can have any possible digit in the first 5 because that's set B, right? We don't care what's going on in the first 5. And I have to subtract out no 7s, right? Which is 9, because I have 9 digits possible to choose from. 0 through 9, but I can't choose 7. So there's only 9 digits to choose from in my second 4. Okay, so let's write this out again. This is our total number. This says any possible number in first 5. And then this part says no 7s in set of 4. Okay, that's our second set of 4. So this is our algorithm, our formula for our NB. Okay, so now what we want to do is this gives us NA and B. We just calculated NT at the beginning. Okay, so the next thing that we're asked to come up with is, let's scroll this down here so you can see. I want to find out their intersection, N, A intersection B. Okay, so this is our multiplication rule. So I'm going to think about this. So this is all outcomes with at least 1 7 in the first 5 spaces and 1 7 in last 4 spaces. Okay, so that's going to look like, right, my first 5, I'm going to go, this is 10 to the 5 minus 9 to the 5. Well, let me write down the math and then we'll talk about what that means. And this is our and. 10 to the 4 minus 9 to the 4. Okay, so what are we saying here? This says all possible numbers in first 5, no 7s in 5 spaces. Okay, this is all possible numbers in last 4, and this is no 7s in the last 4, right here. Okay, so my multiplication rule, let's see, I'm gonna need another page. Let me write this down here, like this. Sorry, I'm running out of space because I write big. I also tend to write a lot of words too. This is example 2, okay? So our multiplication rule, right? We're going to use it on the intersection. So n, a intersect b, right? I'm going to multiply these two together. So this is 10 to the 5 minus 9 to the 5 times 10 to the 4 minus 9 to the 4, okay? So this takes into account both, right? This is where we have at least 1 7 in the first 5 and at least 1 7 in the second 5, okay? So now, let me box this one. Okay, so that gives us our intersection. Now, we want to find our union. A union B. Okay, so what does the union mean? This means, right, we're going to take a look at the total number of zip codes minus the ones with no 7s, in either A or B. Sorry, let's do this first 5 or second 4. Okay, so that's our union, right? So my union is going to look like we did before with how we do this, NA plus NB minus their overlap. Okay, so I'm going to exploit that. So I'm going to fill in, I calculated NA and NB before. We just calculated the intersection. So I'm going to fill in those blanks here. NA union B, the number of their union is going to be, so let's write down our A. So this was 10 to the 9 minus 9 to the 5 times 10 to the 5 plus NB, 10 to the 9 minus 10 to the 5, 9 to the 4, minus, I'll put that bracket down here, minus this whole thing here, 10 to the 5 minus 9 to the 5 times, this is our intersection, 10 to the 4 minus 9 to the 4, bracket. Okay, and then that, oops, sorry, let me scroll that up for you to see. And then that gives us our intersection. Okay, so I'm exploiting what we talked about last week, okay, with how I'm going to combine things, okay, the numbers of things. And we're just going to fill in the blanks with what we had discovered before. Give you guys a second to finish writing. If you've already finished writing, just give me a sec. Okay. So simple 2, I'll save that and I'll scan that in later. Okay, so let's talk about, we're going through a lot of examples. The examples are going to help you kind of pull these rules together and think about how the examples are different. The examples are also going to be a good place for you to compare your notes for when you're doing your homework problems. Some of the homework problems, I did these examples intentionally because they're going to help you when you go to think about how do you solve these homework problems. Okay, so we've got example 3, which is we're going to toss a coin and we're going to roll a die, 6-sided die. We did some of this stuff last week, right? We're going to find the number of outcomes for this sequence of events. Now, because we did this last week, we probably already know like what these are, but let's talk about this in terms of our multiplication rule, okay? So with our coin, let's write down what we have. So our coin, we can get a head or a tail, which is 2 outcomes. Okay, we're told that it's a 6-sided die, right? So I can get a 1, 2, 3, 4, 5, or 6, okay? Which means we have 6 outcomes, right? So our operation A and our operation B, right? I'm going to multiply these two together. My multiplication rule, 2 times 6, is going to give us 12 total outcomes. We saw this last week. We're going to quick draw a graph so we can see what it looks like, just to prove to ourselves that we did it in the right way. It's going to look something like this. So I've got a coin, right? My possibilities are I can do a head, right? When I roll a head, I'm going to roll the die. And so when I do the die, I can get 1, 2, 3, 4, 5, 6. So the combinations here are head 1, head 2, head 3, head 4, head 5, head 6, right? That's our outcomes. Now when I roll the die, I can get a tail. I'm sorry, when I toss the pen, I can get a tail. Then I'm going to roll the die. I'm going to get the same set of outcomes. 1, 2, 3, 4, 5, 6. And this is tail 1, tail 2, tail 3, tail 4, tail 5, and tail 6. We can count them up. This is a really small set. Count them up and only have 12 possible outcomes, which is what we saw when we did the multiplication rule. Okay, so it kind of helps to write things down. What are your outcomes, right? If you can draw a graph, go ahead. It's going to help you think through, are you thinking this thing correctly? Is this the right way to think about it? Okay. Give you guys a second. We roll on to example 4. All right, so example 4 says we've got different types of paint. Like if you ever go into a paint store, you can get all these different colors. We've just limited it to red, blue, white, black, green, brown, and yellow. Oops, there's a W on our yellow. And so I got all these different, I got a type, I can do latex or oil. The texture can be flat, semi-gloss, high gloss. We didn't even include the matte, right? The usage could be indoor or outdoor. There's all, like, we can be overwhelming. Sometimes you go into a paint store because there's so many choices and combinations, right? So we want to know how many different types of paint can you make if you select one, only one from each category, right? Because I'm not going to combine colors. I'm just going to choose one color, one type, one texture, and one use. So basically, I've got the number of categories that I have is equal to 4. 1, 2, 3, 4. 1, 2, 3, 4. So I have color, type, texture, and use as my possible categories, right? So within each category, how many types do we have? Well, I've got 1, 2, 3, 4, 5, 6, 7. 7 for color, 2 for type. I'm counting them up. 1, 2, 3 for texture, and 2 for use. Okay. My multiplication rule says I can choose red, latex, flat, outdoor paint, right? So that's one possible. Okay. So I'm going to multiply all of these together. So these is, I write this down, the number of options for each category, right? And then my multiplication rule says I'm going to multiply all these together. Operation A, Operation B, Operation C, Operation D. 7 times 2 times 3 times 2, multiply it out. I have 84 different types of paint that I can choose, different combinations. Okay, so we're looking at that. This is our multiplication rule here. Okay. We'll do one more example because the example leads into the next topic. All right, example 5. Next page. Let's see, example 5. If we have license plates with 4 digits, so it's nice, right? 2, 3, 4. 4 digits, okay? We want to know, right? I can do 0 through 9. I can put 4 digits because I can do a 0 through 9. So I've got 10 possible combinations, 10 possible numbers that I can choose for each digit, okay? So part A says, how many license plates can you make if repetitions of numbers are allowed? I'll say I did it, are allowed. Okay, so actually I'm going to do part B first. I switched the order when I was typing this up. Sorry about that. So I'm going to do part B first because part A is going to lead us into the next topic. Okay, so if I can make, looks like part A and part B are the same question because I typed it wrong. How many license plate can I make if repetitions of numbers are allowed? So get rid of the not on part A, okay? And part B says if no repetitions are allowed, okay? So part A, I have 10 possibilities for that one. I have 10 possibilities for this space, 10 possibilities for this space, and 10 possibilities for that space, right? I have 0 through 9 possible digits I can do. So this is 10 to the 4, which is 10,000 different types of license plates, which, you know, sounds like a really high number, but we've got like several million people, 4 million people living in Massachusetts. If everybody has a car, we're going to need more numbers or combinations for that. But just as a point of idea, okay, so 10,000 license plates, if I can allow repetitions, okay, for numbers. So I can get the license plate 7777, for example, okay? So part B says, how many license plates can I make if no repetitions are allowed? So let's do our 4 spaces. Okay, so the first space, I have all 10 numbers to choose from. Now, whatever number I chose on that first space, I can't choose again. So I only have 9 numbers left to choose from. Then I can't choose these 2, so I only have 8. And then I only have 7. 10 times 9 times 8 times 7 is going to give me 5,040 different plates. Okay. So part B, no repetitions. I have to take away 1 for each time because I can't repeat that number. Part A, repetitions are allowed. Remember, this is a typo, so cross out that not, right? So I can repeat all these numbers. It's just 10 to the 4. Okay. We've kind of been touching on some of this stuff already, but chapter 2.6 makes it clear, you know, we're talking about all the different rules for combinatorics. All right, so with this example here, let's go into our next topic, okay? Before I give you the second rule, I just want to talk about what's called factorial notation. Some of you may have seen this, factorial notation. In case you haven't, we're just going to discuss it really quick. So factorial means, we call it n factorial, looks like an exclamation mark, n factorial. And what that means is a series of multiplications. I take my n and I multiply it by, I subtract 1 from that n. Then I subtract 2 from that n, and so on and so forth until I get down to the number 1. So if I'm looking at, say, something like 4 factorial, right? This is going to be 4 times 3 times 2 times 1. Okay. We also define, it's important to define 0 factorial as being equal to 1. Okay, it's a mathematical definition, we're defining that. All right, so with factorial notation in place, let's talk about rule 2. In this one, we're going to title it, we're going to count the permutations. And I'll put a little box around it because it's important. Okay, so let's just write in words kind of like what we're thinking about here. So this is going to be, this is when all objects are distinct. So order is going to matter. And then we say, more technically, this is an arrangement of n objects in a specific order. Okay, so let's write down the definition and then we'll start putting it into math terms. Okay, so let's call this the number of permutations of length k, this is a k, of length k, that can be formed from a set of n distinct elements. Okay, we call this NPK. It's also a button on your calculator. I'll bring up my calculator in just a minute. So we'll write out the definition here. So NPK looks like this. This is a formula. N factorial all over n minus k factorial. Now I want to say n is the larger number. Okay, so say I have 4 total and I want to arrange them into a length of 2. So I would have 4 factorial all over 4 minus 2 factorial. And I'd multiply it out and divide it. Okay, so on my calculator here, I'm going to bring up, this is a very, hopefully you guys have a calculator like this. So on my calculator, I've got a math button. So let me bring this up, my math button, right? If I scroll over, it defaults to the math page here. If I scroll over, PRB stands for probability, right? NPR, which is just what we just did with NPK, it's just a different letter, okay? And CR, we're going to get to that in a little bit, that's and choose R, and then exclamation mark, that's our factorial. Okay, so you can do this here. We'll talk about factorial of really large numbers in a little bit. I encourage you to try not to rely too much on your calculator. You want to be able to show the work, okay, for what you're trying to do so that you can get credit for these things here, okay? So also I want to point out that if I do NPN, this is just n factorial, right? Because it's like n minus n factorial, that'd be 0 factorial, which is 1, remember. So it's n factorial, okay? Which is essentially the number of ways, excuse me, to permute an entire set of n objects, okay? Okay, so let's go into some examples so we can see how this actually gets applied. Our second rule. Okay, so example 6, okay, says, how many permutations of length k equals 3 can be formed from a set n equals 4? I'm kind of spelling it out for you, a distinct element, okay? So we can do this just plugging it right into our computations. We can also think about, say I've got, you know, just as an example, 4 distinct elements, for example, say I've got A, B, C, and D, you know, I don't really care what they are, they're just distinct, right? That means I can arrange them, right? I want to put them into 3 sets of 3. So I'm going to have a set of 3 like this. So I can go A, B, C. I can say A, B, D, right? I can say A, C, B. I'm not going to enumerate them all, but you get the idea about how I'm arranging them, okay? So just as an example. Okay, so let's go ahead and think about it. This is n. We want to arrange it into a length of k equals 4. So I'm going to do this. Or choose 3. So I'm going to say 4 factorial all over 4 minus 3 factorial, okay, which is 4 factorial all over 1 factorial. 1 factorial is just 1, right, because it's 1 times, I'm already there, I'm at 1. Okay, 4 factorial is 4 times 3 times 2 times 1, okay, which is 24. Okay? So there are 24 total ways that I can arrange these 4 distinct objects, elements, into a length of 3. Okay. Moving on, example 7 says, for example, we need to pick 2 musical plays, one for a fall production, one for a spring, and we have 9 total plays that we can choose from. So how many different possible combinations can I do, right? I've got something in the fall, something in spring. How do I want to mix these things up? Okay, so I'm going to go 9p2, which is 9 factorial all over 9 minus 2 factorial. Okay, so watch what I'm going to do. This is 9 factorial. This is 9 times 8 times 7 times 6 times 5 times 4 times 3. Well, that sounds an awful lot like 7 factorial, right? 7 times 6 times 5 times 4. I'm recognizing I have a 7 factorial here in the denominator. I'm showing you some shortcuts to make your math a little bit better, right? This is divided by 7 factorial. I can cancel out this whole set because it's still the same set of products and just multiply 9 times 8, which is 72. So I have 72 possible ways that I can choose 2 plays, 2 musicals from a set of 9 possible choices, okay? This here, canceling things out, is going to help you a lot, especially when you're doing factorials with really large numbers, because your calculator is going to max out at a certain point, so you need tricks to be able to cancel things out so that you can make your multiplications a little straightforward. All right, so example 8, moving on. We've got a deck of 52 cards, right? And we shuffle them, and then we're dealing them face up, which means for each card, I just lay it one at a time along the table, right? So I've got a whole set of 52 cards. They're all laid face up, and I want to see, right? So all the cards are showing. We want to know, in how many arrangements will the 4 aces be adjacent, right? So I've got 4 aces, one for each suit, right? So let's think about what that means. So I have 52 total cards. So let's kind of just think this out loud. So I've got the total number of spaces. So I've got 1, 2, 3, 4, 5, 6, 7. I'm not going to write it all 52. So total, and I've got total number of spaces is equal to 52. Okay, but the thing that we're looking for is I've got these 4 aces that are basically operating as a group, right? So I'm just gonna 1, 2, 3, 4. I'm gonna say, okay, these 4 here are our aces, right? And then these here are our 52 minus the 4 aces, right? So this is 48 possible cards left over that I need to arrange, okay? So I've got aces. Now, this actually is just right? If I think about this here, right, as being 1, a block, and then these 48 as being the rest, I have 49 actually functionally spaces that I need to choose from. So 49 functional spaces, right? Because this ace operates as a block, and then I've got 48. So another possibility is I could have all the aces happen first, and then the other 48 cards. Or I can have the first card, and then the block of aces, and then 47 cards, right? So I've got one card here, the block of aces, and then the 47 cards, and so on and so forth. This block of aces is going to be working its way through, okay, as we go along, okay? So now how I need to think about this is, okay, I've got, right, 49 possible ways to arrange this, because I've got this one here, I've got first card, and then the next one, and then I can have 2 cards, and then the aces, and then the other set of them too. So now I've got 49 possible things that I can work with. Within the aces, okay, I've got different ways to arrange the aces. I could do clubs, spades, diamonds, hearts, right? Or I could do hearts, spades, diamonds, clubs. So I've got all those different possibilities within the aces that I need to think about. So let's write down those. So aces can be arranged, right, 4 factorial ways, okay, which we said before was our equal to 24. So aces can be arranged 4 factorial, 4 aces, okay, and then our non-ace cards can be arranged. Well, I have 48 non-ace cards. So I was just talking here about the spacing, but the arrangement of these 48 cards, geez, there's 48 factorial possibilities for how those 48 cards can be arranged, right? So 4 factorial for the aces, 48 factorial for all those different cards, and I have 49 different ways that I can combine this. So I'm going to put all of these together, okay? So the total number of ways that we can make this is 49 for our different possible ways, times the way that the aces can be arranged, times the way that the other 48 cards can be arranged. This is a pretty big number right here, okay, for how many possible combinations can I have, keeping those aces all in a block all the way together, okay? So let's talk about this 48 factorial, okay? Because there's a shortcut. Like, I can do 48 factorial on my calculator. Let's just talk about this for a minute. So I'm going to go 48. You guys can see this, 48, math, over to probability, down to my factorial. You can hit enter. Okay, so it gives me 1.24 times 10 to the 61, right? This means exponent, times 10 to the 61. All right, so 48 factorial, my calculator can handle. I'm just curious, I'm going to do 100 factorial. Oops, it can't handle 100 factorial. It's too big. So I need to have some kind of a way, right? Somewhere between 48 and 100 factorial, my calculator runs out of memory, can't handle it, okay? So we need to have a way to estimate factorials of really large numbers, right? We're going to come up with an approximation. Okay, so we want to have an approximation for when n factorial is very large. Okay, it's too large to actually do computation-wise. Okay, so I'll say my n factorial is approximately equal to radical 2 pi, just the 2 pi is in the radical, times n raised to the n plus 1/2, okay, n plus 1/2, so n.5 times e to the minus n. Okay, I'm not going to go into where this comes from. Okay, our book talks about this a little bit, but I'm just kind of giving it to you as a formula to use when you need to approximate large factorials. Okay, so now how do I solve this? It doesn't really help me. I still have to kind of calculate things out. So what's going to happen is, right, I need to come up with these numbers. So I'm going to take the log base 10 of both sides, right? I know we're tempted to do a natural log because I've got an e here, but bear with me because our numbers are represented as times 10 to the power, okay? So I'm doing it as log base 10. So I'm going to say log base 10 of n factorial, right? Now, because of my rules, my logarithmic rules, right, multiplication becomes addition. So this is log of 2 pi, radical 2 pi. Now this is just a number, radical 2 pi, plus, right, remember our exponent rules, make sure that you group this together, n plus 1/2 times the log base 10 of n plus, actually, sorry, this should be, I was going to say plus minus. This is going to be n log base 10 of e. E is just a number in this case, right? So on my calculator for e, I'm going to go e, and I get, what's my exponent? E to the 1. Okay, that's my e, right, that I'm trying to calculate here. Right, so I plug all of this in. So whatever my n is, right, we'll do an example in just a second. Whatever my n is, 48, 49, something, that's the n that I'm working through. I'm going to get some number. So it's going to be equal to some number, right? But I don't want log of the factorial. I want the factorial. So now I need to, what they call exponentiate it. So I'm going to raise this, raise both sides to 10 to the number, right? I'm going to exponentiate it. So I'm going to say 10 to the log of n factorial equals 10 to the number, right? This is the number that's equivalent to all of this calculation that we just came up with. Remember, these are the same base, so they neutralize each other. So n factorial is approximately equal to 10 raised to that number. Okay, oops, let's go up here. So be careful, you know, when you do this, you're going to be tempted to round a lot, like you're going to get some decimal. Don't round too much, because when I raise that to the as an exponent of 10, those little roundings are going to have big effects. Okay, so keep that in mind. All right, I think, yeah, good. So example 9, we're going to work through, we're going to use this formula to help us work through the calculation for 49 factorial. Like I said, you know, 49 factorial, we can actually probably calculate it on our calculator, but it's reasonable enough for us to be able to approximate here. Okay, so 49 factorial. So in this case, our n is equal to 49. You can start taking notes. All right, so that means I'm going to jump right to where I have the log. I'll write it down like this right here. Okay, so I'm going to say the log base 10, oops, of 49 factorial is approximately equal to the log of radical 2 pi, it's just a number, plus this is 49 plus half, so 49.5 times the log base 10 of 49 minus 49 log of e. I'm putting e in parentheses just so, because it's a letter, right? It makes sense. So this, when I plug it all into my calculator, add it all up, I'm going to get this is equal to 62.78. Okay, I went off to the second place after the decimal place there, but don't round too much. So now I'm going to exponentiate this. I'm going to raise this 10 to the log of 49 factorial, approximately equal to 10 raised to the 62.75, which means, sorry, 49 factorial is approximately equal to 10 raised to the 62.75. Okay, so if I wanted to do something like, just as an example, I want to say something like 24 times 49 factorial, right? I'm going to say this is actually equal to 24 times 10 raised to the 62.75, approximately. It's an approximation, but it's going to help you come up with a calculation, okay? Often a lot of things that we do, we're able to cancel things out, okay, so that we can, because we have things that are being divided by. But just in case you're set up in a spot where you can't cancel things out, you now have a way of approximating factorial of a really large number. All right. So let's move on. We're going to talk about rule 3. All right, so rule 3. This is rule 3 we're going to use, okay, when we want to count the permutations, right, when the objects are not all distinct. So I'll put the rule 3 in a box here. Counting permutations when objects, okay, there we go, objects are not all distinct. Okay, like what does that mean? We'll talk about like exactly what that means. Okay, so now we'll say the number of ways n objects that we have n objects, but the n objects themselves can be grouped, right? Let's see, these are grouped, we'll call that such that, I'll say I've got, I'm going to break down n into little parts. I've got n1 of one kind. So if I have 10 objects, I've got 3 of one kind and 2 of another kind, distinct from n1, and so on and so forth. I've got n sub 3 of a third kind, n sub 4, so on and so forth, all the way down to n sub k of a kth kind. Okay, so I've taken my n total objects, and I've said within this, I've got n1 of kind 1, n2 of kind 2, and so on and so forth. If I sum up all of these n1s, n2s, n3s, so n1 plus n2 plus n3 plus all the way up to n sub k, I'm going to reach my total n, right? Because these things should sum up to the total that we have, total number that we have. So this, right, we want to count our permutations given this kind of a breakdown. I can set it up like this. It's going to be equal to n factorial all over. I break them down. n1 factorial times n2 factorial times n3 factorial times n4 factorial, so on and so forth, all the way down to n sub k factorial. Okay. when I can break up my objects into distinct kinds. Okay. This, by the way, we use this for this is what we call our multinomial coefficients. Right. So say for example, I've got x1 plus x2 plus x sub k raised to the nth. Oh, sorry, I can't even say that. Multinomial coefficients x1, x2, so on and so forth, x sub k raised to the nth power. We'll do an example like this too. The coefficient for a given term right? x1 to the n1, x2 to the n2, x sub k to the n sub k. Okay, we're actually going to do an example like this. So if this doesn't quite make sense, don't sweat it. You'll see it when we actually do the example. Okay, so we'll come back to that. So let's start applying this. I'm going to pull out my example page again. So example 10 says, we're going to do letter permutations. I think you have a homework problem like this too. How many permutations of the letters can be made from the word statistics? This is a good one because look at all the repeated letters that we have. So let's count the letter types. Okay, so I have an S. So how many S's do we have? 1, 2, 3. I've got 3 S's. The next one is a T. 1, 2, 3. I've got 3 T's. I've got an A. Looks like I only have one A. I have an I. I've got 2 I's. And is that it? Nope, I have a C. And I've got 1 C. Okay, so let's add these up. 3 plus 3 plus 1 plus 2 plus 1. This is going to give us, oops, 10 total spots, right? I have 10 letters in the word statistics, right? So these different types, right? This is my N1, N2, N3, N4. These all should add up to the total number of spots that we have. So this is equal to our N. This is N1, N2, N3, N4, N5. So I'm going to put all these together, right? So I'm going to say I have 10 factorial divided by 3 factorial times 3 factorial times 1 factorial times 2 factorial times 1 factorial. I'm putting in the 1 factorial so that you can see that it's going there. You should get in the habit of putting those in too. In reality, 1 factorial is equal to 1, so it's not going to affect the nature of your product so much. But I'm just putting it in so you can see that it's there. You should get in the habit of putting that in as well. So this is going to be equal to, when I multiply it out, I get 50,400, right? Total permutations from the letters in the word statistics. That's like a lot of permutations from just this small word, okay? Let's just write down 1 factorial is equal to 1, just so we know, okay? So a slightly more complex problem. I've got a vending machine, right? And so there's some item in there that I want, right? This is the next example. Some item that I want, it's 85 cents, right? We want to know how many ways can a customer put in 2 quarters, 3 dimes, and 1 nickel. Oh, we're telling you what our N1, N2, and N3 are, okay? And we're gonna, all these things are gonna sum up to 85 cents. This is how we're summing up to 85 cents, okay? So let's think about what we have. So I have 2 plus 3 plus 1. It's gonna give me 6 coins total, okay? Which means I've got 6 spots. 1, 2, 3, 4, 5, 6. So you can think about that as like the order that I'm putting things in. The coins are deposited. Okay, so I've got these plugging it in this way. So I'm going to assign all coins of a particular value, right? So into its own group, right? So I'm going to say N1 is the number of nickels, right? And it doesn't matter. I could have said N1 was the number of quarters. Okay, we're all going to be adding it up. We're just starting up with going from the lowest to the highest. So the number of nickels is equal to 1, right? We were told that at the beginning. N2 is the number of dimes. Okay, I've got 3 dimes. Okay, N3 is the number of quarters. And we have 2 quarters. Okay, I have 6 total coins that I'm putting in, and they each have a breakdown like this, right? So 1 plus 2 plus 3 equals 6. That's a good reality check. Did you break these down correctly? Okay, so the total number of ways that I can do this, right? I would say 6 factorial, 1 for each space, divided by 1 factorial, 3 factorial, 2 factorial. Okay, I'll move that up so you can see it. Okay, so let's just, I'll show you how we can cancel the factorials out. So 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. 1 factorial I'm not going to worry about. So 2 factorial, I'm going to put 2 here because I 3, 2, 1 is being a 3 factorial. 2 times 1, that's 3 factorial. So I'm going to cancel out my 3 factorials, right? 2 goes into, I can multiply it into 4 or 6, 3. And then I'm just going to multiply straight across the top, and I get 60. So what that means is I have 60 possible ways, right, that a person can put in 2 quarters, 3 dimes, and 1 nickel. Okay. So if the coins, let's just do a quick thought experiment here. If the coins were distinct, right, with no categories, like I said, oh, this is a quarter from 1972. This is a quarter from, 1985. Those are going to be distinct coins, say, for example. So I can't group them as this is just the number of quarters that we have, for example, right? Then the total number of possibilities is just 6 factorial, right? Because I have 6 factorial possible ways that I can put in these coins. So then that would be 720 permutations for how I could put in these 6 distinct coins into the vending machine, okay? Or if I just kind of think about quarters as one group, dimes as another group, nickels as another group. Okay, give you guys a second to write that down. Okay. I think you have an example like this in your homework, which is why I wanted to do example 12 in class so that you could see, how you can think about it. Sorry, let's do this so it's a little bit more clear. Okay, so example 12 says, what's the coefficient of x to the 23rd in the expansion of 1 plus x to the 5th plus x to the 9th, all raised to the 100th power? Now, let's just think about that one for a minute. I'm not going to do it all out, obviously, to the 100th power. That would be torture. To the 100th is like saying, okay, I'm going to multiply x to the 5th plus x to the 9th times 1 plus x to the 5th plus x to the 9th times 1 plus x to the 5th plus x to the 9th times, so on and so forth, 100 times, right? So we need to distribute all of these things out multiple times. So that's why we want to have some kind of algorithm for calculating out our coefficients and expanding this so that I don't have to sit here and do it all by hand, okay? So let's think about, we're asked to look at x to the 23rd. Okay, so x to the 23rd. I've got x to the 5th, x to the 9th, and x to the 0, essentially. This is 1, okay? So to get to the 23rd, we're going to need combinations. I'm going to need a 9 times an x to the 9. So 9 plus 9 is going to be 18 times x to the 5th, right? So 18 plus 5 will give me 23. Other combinations, like if I do 5 times x to the 5 times x to the 5 times x to the 5, that doesn't work. X to the 5 times x to the 5 times x to the 9, they don't add up. So this is how we're going to get to x to the 23rd. But because we're expanding this 100 times, I basically need, here I've got only 3 terms, but I need to have 100 terms total. So what else is being multiplied? Its coefficient is 1 times 1 times 1 times 1 times 1, 97 times. Right, so there are 3 terms here. So this is 100 minus 3 gives me 97, right? So this is what I'm working with here. Okay, so the coefficient of x to the 23rd, right, is going to be the number of ways that we can permute this right here. So this is, let's write this down, coefficient of x to the 23rd is the number of ways we can permute this term right here. X to the 9, x to the 9, x to the 5th times 1 times 1 times 1 times 1. Remember, there are 97 ones here. Let me just write 97. Okay, so the coefficient is going to be the number of ways we can do that. All right, so total combinations. This is where I said we were going to come back to that multinomial coefficient. So total number of combinations, watch, I'm going to do 100 factorial, really big number, divided by, right, I've got x to the 9, x to the 9. I have 2, right? So let's write this down. So x to the 9, I've got 2. X to the 5, I have 1. The ones, I have 97 of them. So this is my n1, n2, and n3 that I'm working with here. So this is 2 factorial, 1 factorial, and 97 factorial. I told you before that my calculator bombs out when I try to do 100 factorial. It's probably going to bomb out on 97 factorial as well. So I'm going to be a little bit creative in how I can think about these factorials. So I'm going to say 100 factorial. I've got a 97 here. So I'm going to go 100. Oops, sorry, that's 100 times 99 times 98 times 97 times 96 all the way down to 1. That's actually 97 factorial. And that's divided by 2 factorial is equal to 2 times 1, times 97 factorial, right? I'm not going to worry about the 1 factorial because it's just equal to 1. So now watch, I'm going to cancel off both of these because they're just products that are equal in both numerator and denominator, so they cancel out. The 2, I can just divide into the 100. Oops, sorry. Just 50, right? So 50 times 99 times 98, that's simple enough for me to do on my calculator. And when I do that, I get 48,100, okay? So that's the coefficient of this term here. Okay, so if I were, you can see why you don't want to do this by hand. If I were to do this all by hand, that would be the coefficient of that term when I worked it all the way out, okay? That's our multinomial coefficient. Give you guys a second to write that down. We'll try another example. And then we'll move on to another rule. Okay, so example 13, I'm just going to scroll up a little bit here so you can start looking at it. If you're still copying example 12, I'll scan in our example sheets sometime this afternoon, and then I'll post it onto our Blackboard page so you guys will have that. All right, so we've got a delivery route. So the person's going to start here at point X, and they need to stop, they need to go from X to Y, or beginning and end, but they have to stop at point O, right, somewhere along the way. So how many different routes can be taken if I have to stop, go from X to O, and then O to Y, right? I can go over and up and over, you know, down, whatever. We don't want to go out of our way, right? So I'm not going to go looping all around, but I'm going to go up here, and then I'm going to go from here up to there, okay? So I want to be able to think about what's happening. So let's start, you know, looking at this map, you know, what am I supposed to do? So here's where I'm starting. And this is our first endpoint, right? And this is our, I'll also call it our second start. And this is our final endpoint. Just so I can keep track of what I'm trying to do here, okay? So let's think about it. If I start at X and I go to O, okay, so I'm going to start here. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to go 9 to the right, which we're in a map, so I'll call it, I'm going to head east, just for, you know, kind of keeping it clear. And then from here, I'm going to go 1, 2. I'm going to go 2 up. Well, I'll call it north because we're in a map. An H. Okay. So I start here. I go, my, you know, basically the triangle that I'm making is I need to go 9 over and then 2 up. Okay. And then let's take a look at, we're going to start at O, and then we're going to go to Y. We're going to do the same thing. Okay. So O, I'm going to go 1, 2, 3, 4, 5. So I'm going to go 5 east, 1, 2, 3, and then 3 north. Okay. So let's think about it. Let's do our different combinations here. So we're going to go X to O. Okay. So when I go X to O, I need to go 9 plus 2 total boxes, right? Total boxes, which is 11. So that gives us our numerator. That tells us how many total boxes that I need to move, but I'm going to go 9 factorial times 2 factorial because I've got 9 of the category going east and 2 of the category going north. Okay, so this is going to look like 11 factorial all over 2 factorial times 9 factorial. And I can multiply it out because 11 factorial contains a 9 factorial. And I can, multiply things out. This is small enough you can probably do it on your calculator. I'm going to get, when I do this out, I get 55 total. Just going from X to O. This is why you don't want to like sit here and try to count them out yourself. Okay, so we're coming up with a way to think about it. So let's think about when I go from O to Y. We're going to do the same thing, right? The groupings that I have 5 categories going east and 3 categories going north. But I'm going to go 5 plus 3 is 8 total. There are little notes here, 8 total. That gives us our numerator. So let's write that out. I've got 8 total boxes that I need to go in. 5 of one type, 3 of another. And when I multiply all this out, I get 56. Now remember the original question that we had to do. I have to go X to O and then X to Y. So I'm going to use my multiplication rule. I can spell multiplication rule. And I'm going to multiply 55 times 56 because that gives me my X to O and X to Y. And when I multiply that out, I have 3,080 total roots. This is why you don't want to count them out yourself. You want to have a way of thinking about it. Okay. Give you a second to finish writing that down.
I have a question in the previous one.
The multinomial one? Yeah.
Yes. How did you get the number of x to the 9th and number of x to the 5th and number 1?
Yeah, so I know that the number of terms here has to sum up to 100, right? Because that's what we're multiplying out here. And then those are the total number of things I have to multiply together. How do I do this, right? This is going to depend on what numbers are going to help me sum to 23. So 9 plus 9 plus 5 is going to help me get to 23, given that I only have an x to the 5 and an x to the 9, right? I mean, like if you were to just do this out, like say you just did this out to like the third, where you could actually enumerate everything out and prove to yourself that you're doing it right, then you can kind of think you can get the numbers to line up because it's a small subset, and then we can extend to a larger number here. The whole point in choosing 100 is that we can't enumerate it easily, right? So I need this by the power of exponents, right? When I think about how am I multiplying through, I've got a 1 times 1, plus a 1 times x to the 5th, plus a 1 times x to the 9th, plus x to the 5th times 1, you know what I mean? You can see where things are going. So all of these different combinations come from how I'm distributing these multinomials, right? These trinomials together. And I do this 100 times, right? So I've got a whole combination. So x to the 23rd is one of my exponents within here because it's one of the possible sums for the combinations that we have. So 23 comes from summing my exponents, right? And that, go ahead.
Oh, no, I was saying, yeah, I understand.
You got that? Okay.
Yes, thank you.
Yep. And like I say, often when I'm faced with something like to the 100th and I can't multiply it out myself, I'll take this myself and I'll make it to like the squared or to the third term, and then I'll multiply it out because then I can see what all the different terms look like, right? And then what are the different possible combinations? What are the coefficients? How does it add up? And then I'll see how does the formula look when I only have to the third power, because I can prove it based on how I've distributed it and based on the formula that I'm trying to work my way through and thinking about things, okay? And then I can start off with something small so that when I make this number, this overall exponent bigger, then I can see how the formula is going to hold together. That can help. Just start off with something small that you can prove and then see if it'll generalize, which in this case it will. All right.
I think.
Yep. Okay, so one more thing on this particular rule I just want to mention too. There's a thing called circular permutations. I can't remember, I think you've got one like this in your homework, I can't remember. But it's basically a nonlinear arrangement. And you can think about, so objects are not lined up in a row. Let's write that. Objects are not lined up in a row. Okay, so you can think about like seating at a table. Right, I've got a round table and I want to be able to, I've got like 5 people who are going to sit there. So I've got this, but it's circular, right? Because this person here is sitting to the person next to them, right? So I've got to be able to think about this. When I have a circular permutation, the number of possible combinations is n minus 1 factorial. Okay, so this is the number of ways to arrange n objects in a circle. Okay, like, pistons firing in an engine, oops, sorry. You see that? N objects in a circle. It's n minus 1 factorial is how we're thinking about it in a circle. Okay, I'm not going to spend too much time on that, but because it's just a little blip here, but you may have a homework question on that just to kind of think about it. All right. Great for you guys to have that. And then we'll move on to rule 4. Okay. All right, so get this lined up here. Okay, so rule 4, okay, is again about counting combinations. It's slightly different. We're going to summarize all these different rules at the end, so you can see how they're different. So counting combinations. So we do this. Let me just write this down and we'll talk about. Okay, so the concern is with the composition of a set of elements, not with any particular order. How can we make up this thing? So what we're going to say is we've got k unordered elements. We're going to call this a combination of size. That's a size k. Okay. So what this means is, I write this out. This is a theorem, but I'm just going to write it out. So we're going to say this is the number of ways. This is our theorem. The number of ways to form combinations of size k, that's a k, from a set of n distinct objects. And we're not going to allow repetitions. Okay, so how we write this is, you've probably seen this before. This is called n choose k. We write this as n ck, where n's bigger than k, or n can be bigger than or equal to k. And this is, I'll write this out as n choose k. We write it like this, n factorial all over k factorial times n minus k factorial. This is part of our binomial expansion. You guys have probably seen this in our binomial coefficients, okay? We think about this like the number of objects that we're taking out of a bucket, or as your book calls it, an urn, and we're not replacing them, right? There's no repetition. So we're going to need these combinations here. Incidentally, the n choose k is our permutations divided by our k factorial, okay? Just so you can kind of see where these things are building on each other. This is also on my calculator. So I've got math. Oh, sorry, let me show you. So I hit my math button. And it's going to open up a window. I go over to the probability window, and I've got NCR. That's our n choose. What we call n choose k, they're calling it n choose r. Just different variables. Okay. I encourage you though, make sure that you're showing your work. Okay, so that you don't just plug it into your calculator. Right. Okay. So let's go back to our examples, and we'll think about what we're going to do. So starting off here, oops, sorry, example 14. So example 14 says, how many combinations of 4 objects are there taken 2 at a time? So we're kind of setting this up for you. So in this case, right, we've got n is 4 and k is equal to 2. So I have 4, choose 2, right? I've got 4 objects total. I want to take them 2 at a time. How many, different combinations can I do that in? So I've got 4 factorial all over 2 factorial all over 4 minus 2 factorial, which is 4 factorial, 2 factorial times 2 factorial, okay? which is just going to be equal to 6. Okay. And you multiply it and divide it through. Okay. All right, so let's make this a little more complex. Let's think about, we've got 8 people, okay, and they're going to shake hands with each other. Okay, and we're not going to have repetitions because you don't shake hands with yourself, right? And you need 2 people to shake hands. Okay, so we want to find out how many handshakes are there going to be. Okay, so let's think about it. So I'm going to write down 2 people needed for a handshake. Okay, and no repetitions, right? So what I'm going to say is I've got 8, choose 2, right? So how many combinations of a handshake can I possibly do with 8 people and no repetitions are allowed? So I'm going to set this up, 8 factorial all over 2 factorial, 8 minus 2 factorial, okay, which is 8 factorial, 2 factorial, 6 factorial, okay. Let's just multiply this out so you can see. So 8 factorial is 8 times 7 times, oh look, 6 factorial, 6 times 5 times 4 times 3, that's all 6 factorial, all over 2, right, because 2 factorial is just equal to 2, times 6 factorial. So these will cancel, okay. This 2 divides into the 8 4 times 7 is equal to 28. So we have 28 possible handshakes that we can do, okay, given 8 people, okay, and no repetitions. Okay. All right, let's try. Let me move this down. Example 16 says, we have a committee, right? In this club, we've got 7 women and 5 men. We want to make a committee of 3 women and 2 men, right? So how many different possibilities are there that we can do? So let's think about it. So I'm going to separate out the women from the men because we're saying, right, I want to have in this committee 3 women and 2 men, basically choosing half and half. So I'm going to select 3 women from a pool, 7 total. Okay, so I need to think about the different combinations that we're going to do. So this is 7, choose 3, okay, which is going to be 7 factorial, 3 factorial, 7 minus 3 factorial, okay. When I multiply everything out on here, this is going to give me 35 possible ways to choose 3 women from a total of 7. We're going to do the same thing for the men. So we're going to select 2 men from, what do we say, 5 total. Okay, so this is going to equal 2. 5, choose 2. Okay, 5 is my total, 2 is what I'm choosing for. So I'm going to set this up as 5 factorial all over 2 factorial, 5 minus 2 factorial. Okay, when I subtract and multiply everything through, I have 10. Okay, so I have 35 ways to do the women and 10 ways to do the men. Our multiplication rule says I'm going to multiply the total number of women that we found times the total number of men combinations that we found. So this is 35 times 10, which gives us a total of 350 different possibilities that we can choose this particular committee. Okay. All right. So our last example is a good one right before lunch, which is about sandwiches. Food is always a good example. All right. So we've got this. We're going to order a sandwich, and it has 8 extra toppings. We have lettuce, tomato, onion, mustard, ketchup, mayonnaise, pickles, and peppers. Okay. We want to know how many different sandwiches can we order, and we're just going to assume that we're only just using one type of meat. Right? So pick whatever type of meat you like, and then you're going to think about these 8 extra toppings. Okay. So let's think about this. So part A says, how many different sandwiches can we order, assuming only one type of meat? And then let's say we distinguish each sandwich by the total combinations, different combinations that we can choose for each different topping. Okay, so let's think about this one, right? So I'm gonna, the question I want to ask is, do you add a topping? Right, I can do yes or no. These yes or no questions are really important. They're going to form the basis for our statistical analysis later, right? Where I have this, binary event. Is it yes or no? So I have one of 2 possibilities. So do I add a topping, yes or no? So I've got 8 possibilities. So I've got 1, 2, 3, 4, 5, 6, 7, 8. So this is for our lettuce. This is for our tomato. This is onions, mustard, ketchup, mayonnaise, pickles, and peppers, right? So do I want to order a topping, yes or no? Okay, yes or no. I have two possible outcomes, right? Yes or no. So I have 2 for that one. I've got 2 for this one. 2 for each of these, right? Because I could say yes or no on each of these. And I've got 8 possible things, toppings. So basically I'm multiplying 2 times itself 8 times, which gives me 256 total possibilities, okay, for different types of sandwiches that I can do. Sorry, this is part A. So now for part B, we want to distinguish each sandwich by its particular combination of toppings, right? So do I want lettuce and onions but nothing else? So I want lettuce, tomato, onions but no mayonnaise, whatever, you get the idea. So how many toppings are we trying to do? And then all the different permutations for those different types of toppings. So for here, we're going to sum up all the possibilities. Okay, and I'm going to write down what our different possibilities are. So I've got 8 possible toppings, and I don't want any of them. 8, choose 0. Okay. I've got 8 possible toppings, and I only want 1. You see where I'm going with this. 8 possible toppings, and I only want 2. This N choose K allows me to say, do I want lettuce and mayonnaise? Do I want lettuce and ketchup? That's how I'm arranging. I've got 8 possible, and I only want to choose 1. So that's going to tell me how many of those different possibilities I'm going to do. So I'm going to do this for all of them. 8 choose 7 plus 8 choose 8, right? These are our total number of possibilities that we can do. Each one of these is one of these N choose K possibilities, right? I would multiply it all the way up and I'd sum up all these answers. And if you go through this, you'll find that you actually have 256 total possibilities as a result of distinguishing each sandwich by its different combinations. Okay, this is what we would call, if I'm going to write this out in math, I'm going to say I've got this sum. Right, I'm going to go K starts at 0 to N. Right, I'm going to do N choose K. Okay, and if I only have 2 different possibilities, this ends up as 2 to the N. Yes, we'll call it yes/no outcome. Right, and this is kind of like our binomial expansion, right? I'll just say tie this back into some other stuff. So binomial expansion. We did this, right, where I have x plus y to the nth power. This would be sum equals k equals 0 to the n, n choose k, right? I've got x to the k, y to the n minus k, right, as my variables here. Now let's say what we're going to let x equals y equals 1, right? So each one, what am I going to do? This becomes 2 to the n, right, because 1 plus 1, 2 to the n, right? And that's where we get this value here, which is our 2 to the n. Okay. Summing up the possibilities is something that we're going to be thinking about as we go. Okay, give you guys a chance to finish writing that down, and then I'm just going to summarize the different rules, okay, into a table so that you kind of have it. You can kind of think about, you know, what's the rule, what's it called, what's its brief definition, and what's its formula. Like, why is this important? Okay. Start a new page for that. So let's see. So we'll do our summary of our rules. We had 4 rules. Okay. So our first rule, so this is our rule here. Then we're going to have a definition. And then we'll have the formula. Here is our third column. Okay. So rule 1 that we did was our multiplication rule. Okay, so our definition for this, remember, make this clear. This is going to be the number of ways a sequence of n events can occur if the first event can occur in k sub 1 ways, and second event can occur in case of 2 ways. Okay, our multiplication rule says we're just going to multiply all these together. So this becomes case of 1 times case of 2, all the way up to how many are we enumerating? Okay, that's our multiplication rule. Okay. The second rule, rule 2, trying to leave both up there so you can keep writing. Our rule tool says we're going to count our permutations. Oops, I'm running out of space. Count our permutations. So this is our first rule of counting permutations. Okay, so this one, we have the number of permutations of n objects taking k objects at a time. In this case, order is important. Okay, so order is important, right? And this is our n permute k, which is equal to n factorial all over n minus k factorial. That's our first rule of counting permutations, which was our second rule total. I'll scroll that up. Okay, our rule 3, which was also counting permutations. This is our second rule for counting permutations. Okay, in this case, right, we're doing the number of permutations of n objects when we have n1 objects of one type and 2 objects of a second type, and so on and so forth. Okay, I can have up to however many objects I'm going to have. Okay. All right, now I'm going to set this up as n factorial all over n1 factorial times n2 factorial all the way up to n sub k factorial. Okay. Order is important, not necessarily order is important on our second counting rule. Okay, for our fourth rule total is counting combinations, not counting permutations, but counting combinations. So what this says is the number of combinations of k objects, oops, I'm not spelling this right, OBJ, objects taken from n total objects. And this one, order is not important. Okay, this is our n choose k, which is equal to n factorial, k factorial, n minus k factorial. Okay, so our summary, okay, it helps to kind of tabulate it and put it into a summary for the different types of rules that we've been working with and talking about. Okay, so here's rule 3 and 4. I'll leave this up here because hopefully you have done rule 1 and 2, but I'll post the video for this class later today. Okay. Just a quick side note before we sign off, make sure tomorrow when you come to class, I think we'll be able to do chapter 3.2 and 3.3 in one lecture. They're both shorter than the stuff that we've been doing. So print out your lecture example pages for both chapters, because if we get a chance to roll into the next chapter section, then I'm going to take advantage of that. Okay. All right, you guys. Go ahead and start. I think I put up a new assignment over the weekend for our second set of homeworks, which include homeworks for chapter 2.6. You can go ahead and start looking at those. I have office hours today at the usual time if you wanted to stop by and ask any questions about stuff, and then we can talk about it. Okay. All right, you guys.
Thank you.
Bye-bye.
Thank you.
Oh yeah, I also figured out the homework thing. I was just pressing the wrong buttons.
So let me pause the recording here.